Welcome to Modern Physics Lab 2. In this lab, we will be studying the effects of the drag force on an object that is dropped from a certain height. We will use Tracker to study the observed motion. We will then create a computer model to compare our real-life example to the theoretical removal of drag force and one with drag force accounted for. Because of the drag force countering the weight force, the net force is not exactly equal to the force of gravity. Drag itself is not a constant force across every object. Objects with more surface area, like a flat piece of paper, may encounter far more drag force than other more aerodynamic objects, such as a rock. In order to fully witness the effects of drag, I chose to drop a blown-up Ziploc bag. This object falls relatively slowly because of the magnitude of the drag force. We wish to examine this because it will exaggerate results for comparison. We care about the drag force because of its importance in real-life applications, such as the existence of a terminal velocity and the need for aerodynamic designs. Here you can see my video of me dropping the Ziploc bag. Tracker is used to translate the data into a table for later comparison with my computer models. I chose the part of the video that would be easiest to track before hitting the ground. The tracker model demonstrated not only a change in the negative y-hat direction, but also along the x and z axis. The camera angle may have also distorted the movement. However, it is clear from the beginning that the drag force was a factor in the demonstration. I could have improved my data by incorporating multiple takes and attempting to use one that limits movement in the x and z direction. Following the gathering of the observational data with Tracker, I created a model that neglected the effects of drag. This is indicative of how an object in a vacuum would fall. I utilized the formula F of grav is equal to Fg times the mass in the negative y-hat direction for the force of gravity. I also made sure to use position and velocity update formulas with each iteration of the while loop. Notice the absence of the drag force in the code. For my second model, I made sure to incorporate the drag force within the template of the first model. For the purposes of this lab, drag is defined as the square of the velocity in the opposite direction of the force of gravity. Note that the proportionality constant b is also included in the calculation. This was calibrated using the final values from the observed data. It is clear that the object falls much slower in this version of the model. Similar to the first model, I ensure to update position and velocity for each iteration. As you can see, the drag force is relatively large, which is why the object falls slowly. Comparing all three sets of data, it is clear that the model that incorporated drag force is very close to the observed data. However, the model that neglected drag force is way off. This is because velocity never slows due to the gravity acting unchecked. For small time steps, this matters very little. However, as time increases, the models differ increasingly. As stated previously, expected movement was much quicker than observed when drag is neglected. This is especially true because the object that is very prone to drag force was used. In addition to this, camera angle and additional movement in the x and z directions may have distorted results. In order to further emphasize the effects of drag, I've created a velocity versus time graph comparing the two different models. Clearly, the model without drag force accelerates constantly for an infinite amount of time. However, the addition of drag means that drag became equal to the force of gravity. This is when an object reaches what is known as terminal velocity. The graph begins to flatten, and the terminal velocity is approached only in the drag model. The next graph compares the effects of throwing an object downward on terminal velocity. As can be seen, this does not change the terminal velocity. It only changes the time an object takes to reach the terminal velocity. The pink line on the bottom begins at a greater velocity and therefore reaches terminal velocity a lot quicker.